Welcome to today we would discuss CMOS and NMOS process technology, two of the most important transistor fabrication methods in the semiconductor industry. We'll explore how these processes work, their fabrication steps, their advantages and disadvantages, and why the industry favors one over the other in most applications today. We'll also discuss current and future trends in process scaling and integration. Before diving into the details, let's quickly recap what MOSFET technology is. MOSFETs are the building blocks of modern digital circuits, consisting of a gate, a source, and a drain separated by an insulating oxide. In NMOS technology, circuits are built entirely with N-type MOSFETs, whereas CMOS, which stands for complementary MOS, uses both N-type and P-type devices. The main difference lies in power consumption, speed, and the complexity of fabrication. This difference in architecture has major implications for efficiency and scalability. NMOS technology relies exclusively on N-channel MOSFETs, which are formed on a P-type substrate by diffusing or implanting heavily doped N+ regions for the source and drain. Logic levels are implemented with pull-up resistors or depletion mode NMOS transistors acting as loads. NMOS transistors have higher electron mobility compared to holes in PMOS, which makes them faster. However, the design suffers from higher static power consumption because a current path exists whenever the output is low, leading to constant power drain. In CMOS technology, both N-type and P-type MOSFETs are fabricated on the same chip. This requires creating wells of the opposite type in the substrate. For example, N wells in a P-type wafer for PMOS transistors. One of the greatest strengths of CMOS is that in steady-state logic conditions, ideally, no direct path exists between VDD and ground, which means very low static power consumption. This makes CMOS particularly suited for battery-operated devices. Additionally, CMOS gates exhibit symmetrical switching behavior, leading to robust logic design and high noise margins. The NMOS fabrication process begins with a P-type substrate. A thin gate oxide layer is grown thermally to insulate the gate. Then, polysilicon is deposited and patterned to define the gate electrodes. The source and drain are formed by diffusing or implanting N+ dopants. After that, an interlayer dielectric is deposited to isolate metal layers from the silicon. And finally, metallization is performed to interconnect the transistors. The simplicity of NMOS fabrication compared to CMOS was one reason it dominated early microprocessors in the 1970s. The NMOS fabrication process begins with the growth of a silicon dioxide (CO) layer on the silicon substrate through thermal oxidation. This oxide layer serves as an insulating and protective mask for subsequent steps. Using photolithography, a photoresist is applied and patterned to define the active regions where the NMOS device will be formed. The unwanted oxide is then etched away, exposing the silicon surface in those active areas. Next, a thin gate oxide is grown specifically over the channel region, providing the essential insulation between the gate electrode and the underlying silicon. Following this, the gate oxide is patterned to create windows for the source and drain regions, enabling precise doping in these areas during the next fabrication stages. After the gate oxide is patterned to open windows for the source and drain, N-type dopants are introduced into these regions using diffusion or ion implantation, forming the highly conductive N source and drain areas. Next, a fresh oxide layer is grown over the wafer to provide isolation and protect the surface. But contact windows are carefully left open above the source, drain, and gate regions to allow electrical connection. The metallization process then deposits a thin metal layer, usually aluminum, across the wafer. This metal layer is patterned so that it remains only in the contact windows and connecting paths, establishing electrical terminals for the source, drain, and gate. These steps complete the basic NMOS device structure, making it ready for packaging or further integration into circuits. The CMOS process is more complex because we must form two types of transistors. In a typical N-well process, We begin with a P-type wafer and use photolithography and ion implantation to create NVELs where PMOS transistors will reside. Gate oxide is grown, followed by polysilicon deposition and patterning for gates. The source and drain regions are then implanted with the appropriate dopants for each transistor type. After isolation with a dielectric layer, we carry out metallization to connect devices. The added complexity increases cost but enables superior energy efficiency. In this CMOS fabrication process, the left side of the diagram illustrates the step-by-step physical changes in the wafer, while the right side shows the corresponding mask patterns used at each stage. We start with a P-type substrate, which serves as the base for the NMOS devices. For PMOS devices, an NVEL is created by introducing N-type dopants into selected regions of the substrate. Once the wells are defined, oxide and nitride layers are grown over the wafer surface and patterned appropriately to define the NMOS and PMOS active areas. To control leakage currents and improve isolation, channel stop implants are introduced using P-doping in specific regions. After that, a thick field oxide is grown and patterned to isolate devices from one another. Next, a thin gate oxide is formed in the channel areas, and polysilicon is deposited and patterned to create the gate electrodes for both NMOS and PMOS devices, with PMOS gates located inside the NVEL. This brings together the final device structure of a CMOS inverter in cross-sectional view. If you look closely at the picture, you can see both the NMOS and PMOS transistors that form the inverter. The NMOS device is built directly into the P-type substrate, while the PMOS device is fabricated inside an NVEL that is diffused into the same substrate. This arrangement is typical of the NVEL CMOS process. Notice that each transistor has its gate, source, and drain regions clearly defined. The gates are formed by the polysilicon layer running across the channel, separated from the silicon by a very thin gate oxide. On either side of the gate, heavily doped source and drain regions are formed, N+ regions for the NMOS and P+ regions for the PMOS. Now, if you look carefully at the electrical connectivity, you'll see how the inverter is implemented. The drains of both transistors are shorted together, and this common connection serves as the output node of the inverter. The source of the NMOS is tied to ground, while the source of the PMOS is tied to VDD. The gates of both devices are connected together as the input terminal. This complementary arrangement ensures that when the NMOS is on, the PMOS is off, and vice versa, giving the correct inverter transfer characteristic. On the right-hand side of the picture, you can also see the masks used during fabrication. Each mask corresponds to a specific process step for defining wells, active areas, gate patterns, source-drain implantations, and metal interconnections. These masks act like blueprints, ensuring that every feature is precisely aligned and etched or doped in the correct location. So, this essentially summarizes the full CMOS inverter fabrication process. It starts with the substrate and wells, moves through gate formation, doping, and interconnects, and finally arrives at this integrated structure of NMOS and PMOS transistors working together. The side view gives us a clear visualization of how the two transistors are placed side by side in silicon to form one of the most fundamental building blocks of digital VLSI circuits, the CMOS inverter. A CMOS inverter is built using two transistors, an NMOS at the bottom and a PMOS at the top. Both devices are essential because they work in a complementary fashion. When one is on, the other is off, which is the key to low-power, high-noise margin digital logic. There are a few important things to note in this schematic. First, each MOSFET must have a body connection. For the PMOS, the body is tied to VDD through the NVEL, and for the NMOS, the body is tied to ground through the P substrate. These body connections are crucial to prevent body effect and ensure proper transistor operation. Next, notice that the gates of both the NMOS and PMOS are connected together. This common connection forms the input terminal of the inverter, usually implemented using a single polysilicon line running across both devices. Similarly, The drains of the NMOS and PMOS are tied together. This shared drain connection becomes the output node of the inverter, and in layout, this is usually realized using a metal line that connects both drains. Finally, the source of the PMOS is connected to VDD, and the source of the NMOS is connected to ground. This arrangement guarantees that whenever the input goes high, the NMOS conducts and pulls the output low, and whenever the input goes low, the PMOS conducts and pulls the output high. Let's now talk about the first major step in CMOS fabrication, which is creating the N-well for the P-channel devices, along with the channel stop implants that help control leakage in a detailed manner. The picture shows the various stages involved in creating an N-well. To do this, we need to go through two complete process steps involving photolithography. First, we coat the wafer with photoresist and expose it through a mask to define the regions where the N-well will be formed. But here's something very important to note. The photoresist layer by itself is not enough to shield the silicon from ion implantation. The energetic dopant ions can actually penetrate right through it. That's why we use a combination of oxide or nitride layers as implant masks. These materials are strong enough to block the incoming ions and prevent doping in unwanted regions. Once we've completed the implantation in the exposed areas, the hardened photoresist needs to be stripped away. And for this, we use solvents like acetone. If we want to remove the oxide or nitride layers that were used as the hard mask, we can also etch them away after the implantation is done. One key requirement is that the oxide or nitride layers must be thick enough to fully block the dopant ions during the implantation step. Otherwise, some ions might still punch through and contaminate areas that should remain undoped. In fact, the ions used in implantation are so energetic that they actually travel through the photoresist and stop only when they hit the oxide or nitride barrier underneath. This is why the combination of photoresist plus a thicker oxide or nitride mask is essential to achieve precise and reliable well formation. So, this step, N-well creation with proper masking and channel stop implants, sets the foundation for correctly isolating the PMOS and NMOS devices in the CMOS process. Asterisk. The next step in CMOS fabrication is the growth of the field oxide, which builds on top of the previously formed channel stop implants. This step is crucial because it completes the isolation regions that electrically separate different transistors on the same chip. Now, here's what happens. We use a layer of silicon nitride to protect the active regions. Since nitride does not allow oxidation, no oxide grows in these areas. That means the field oxide only grows in the unprotected regions where we actually want the isolation. Once the field oxide growth is complete, we need to strip away the nitride and any residual oxide layers. This requires another photolithography step. Interestingly, the mask used at this stage is essentially the negative image of mask number 2. Because of this, we can take advantage of negative photoresist and reuse mask number 2, which helps in saving an additional reticle. And in semiconductor manufacturing, saving masks translates into reducing cost. When this sequence is finished, the wafer has well-defined active regions. These are the exact spots where the MOSFETs will eventually be fabricated. The field oxide, which is much thicker than the gate oxide, surrounds these active regions, ensuring that the devices are properly isolated from one another. So, to summarize, this step, growing the thick field oxide, removing nitride, and defining the active areas, is what enables us to precisely decide where each transistor will exist on the chip. From here, we can now move forward into building the MOSFET structures themselves. Asterisk. Now that the active regions have been defined, the next critical step is the formation of the gate material. For this, we deposit a thin layer of polysilicon across the wafer surface. The deposition is typically done using a process called chemical vapor deposition, or CVD, which allows us to form a uniform, conformal layer even over uneven surfaces. This polysilicon layer will ultimately become the gate electrode of our MOSFET. The gate is the control terminal that modulates the channel conductivity between the source and drain, so this step is fundamental to device operation. In some older or specialized technologies, metals like aluminum were directly used as gate material. However, polysilicon is generally preferred because it can withstand the high-temperature steps that come later in the fabrication process. In modern processes, you may also see polysilicon replaced or combined with metal gates to reduce resistance. Once the deposition is complete, the entire wafer is covered by polysilicon. But we don't need it everywhere. Only in specific regions where the transistor gates are located. To achieve this, we apply photolithography followed by a dry etch process. Dry etching is highly directional or anisotropic, meaning it removes material vertically while leaving the side walls intact. This gives us sharp, well-defined gate structures. At the end of this step, we now have the patterned polysilicon gates sitting right above the thin gate oxide aligned with the active regions. These gates will serve both as the electrical control contacts and as masks for the next doping steps that form the source and drain. At this stage of the CMOS fabrication process, we move on to the implantation or doping of the source, drain, and body contacts. This is one of the most critical steps because it defines the fundamental electrical terminals of our MOSFETs. Let's begin with the polysilicon gates we deposited earlier. By default, polysilicon has a relatively high resistivity, which makes it a poor conductor. To make it function effectively as a gate electrode, we need to dope it heavily, either with N-type or P-type dopants, so that it becomes a low-resistive path for carrying signals. Now, when we form the source and drain regions, we also have to pay careful attention to the body or substrate connections. For an NMOS transistor, the body terminal, that is, the P-type substrate, is tied to the same potential as the source, which is ground. For a PMOS transistor, the body, located in the N-well, is tied to the same potential as the drain, which is VDD. This ensures proper biasing and avoids unwanted parasitic effects. But there's an important detail here. When you place a metal contact directly on a lightly doped semiconductor, it usually forms a Schottky barrier diode instead of a good electrical connection. This is undesirable because the Schottky diode has a nonlinear IV characteristic which interferes with circuit operation. What we need instead is an ohmic contact, which behaves like a simple resistor with a linear IV relationship. To achieve this, we must heavily dope the semiconductor region under the contact. For NMOS devices, this means using P+ doping in the substrate for the body contact. For PMOS devices, we apply N+ doping inside the N-well for the body contact. This heavy doping lowers the barrier height and ensures that the metal contact forms an ohmic connection, enabling reliable current flow into and out of the source, drain, and body regions. So, by carefully implanting these dopants and aligning them with the gate structures, we create the source, drain, and body terminals that make the MOSFETs fully functional. Now that the source, drain, body, and gate regions have been formed, we move to the final critical step of creating electrical connections, adding the metal contacts. The first thing we do here is to deposit a thin insulating layer of silicon dioxide, CO, over the entire wafer. This is done using chemical vapor deposition, CVD. Notice that this time we are depositing the oxide, not growing it. The reason is simple. At this stage, we no longer have access to the bare silicon wafer surface, so thermal growth of oxide is not possible. Instead, deposition provides a uniform insulating layer over everything: the transistors, the gates, and the field oxide regions. Next, we need to create openings, known as contact windows, at specific regions where the metal will connect to the source, drain, body, and polysilicon gates. We achieve this by using another photolithography and etching step, which selectively removes the oxide only at the contact points while leaving it intact elsewhere. Once these windows are defined, we proceed to deposit the metal layer. Typically, aluminum is used, though in advanced technologies copper is preferred. The deposition is done over the entire wafer, often through metal evaporation or sputtering, processes very similar in concept to CVD. At this point, the wafer is fully covered with a uniform sheet of metal. But again, we don't want metal everywhere, only as interconnect lines and terminal pads. So, we use yet another photolithography and etching process to pattern the metal into the required shapes. This defines the wiring that connects each MOSFET terminal to others, or to power and ground rails. This first patterned metal layer is called Metal 1. In modern ICs, there may be many additional metal layers stacked on top, separated by insulating layers, to handle the enormous routing complexity. But Metal 1 always refers to this very first interconnect layer. One final note: when this metal is deposited, it lies on top of a very non-planar surface. You can imagine it having bumps and valleys from the transistors, field oxide, and polysilicon structures below. This non-planarity can affect the uniformity of the metal. So later in advanced processes, techniques such as planarization, CMP, chemical mechanical polishing, are used to smoothen the surface before stacking multiple metal layers. So, by completing this step, we have successfully formed the metallic connections that make our transistors functional parts of an integrated circuit. This table summarizes the main differences. NMOS offers high speed due to higher electron mobility but suffers from high static power consumption. CMOS balances speed with extremely low power consumption, which is why it has become the dominant choice in the semiconductor industry. While CMOS fabrication is more complex and costlier, the benefits in terms of scalability and energy efficiency outweigh these drawbacks for most applications. In short, NMOS's advantage lies in speed and simpler manufacturing, while its disadvantage is high power dissipation. CMOS, on the other hand, dominates in efficiency and scalability but comes with a more intricate manufacturing flow and a higher initial cost per wafer. Today, CMOS is unquestionably the industry standard for digital integrated circuits. It's used in virtually every microprocessor, memory chip, system-on-chip, and ASIC. NMOS still exists in niche roles, particularly in some high-speed analog applications, but its use has dramatically declined. The shift toward portable, low-power electronics over the last 3 decades cemented CMOS's dominance. Looking ahead, CMOS technology continues to evolve. Process nodes have shrunk to 5 nanometers and are moving toward 2 nanometers, with planar transistors giving way to 3D structures like FinFETs and gate-all-around FETs. These advancements aim to balance power efficiency and performance as we approach physical scaling limits. Research into integrating CMOS with emerging devices such as carbon nanotube FETs and two-dimensional materials is ongoing, potentially enabling new breakthroughs in computing.